Thank you. Thanks for letting me give this presentation. Unlike the previous two gentlemen who are real engineers, I'm a sales guy. And so I want to share with you some of the things that I've learned late in my career. About 7 or 8 years ago, I went to work for Ferrite Products. And I have to apologize. Normally, I would take the branding off. But what I want to cover today is really applicable to all ferrite manufacturers. Retired about 2 years ago, and I still work as a product consultant for Ferrite. I wanted to cover a number of topics today because probably about 3 to 5 questions a week come into our company, and I can tell by the nature of the questions, there's a lot of confusion about how ferrites work, what ferrite I should buy, even where I buy it. So I want to cover some of these things. So I'm sure some of you have bought a ferrite out here at the Hamvention from somebody who has a pile in the trunk of their car. You took it home, you put it on a cable, and it probably might have worked, might not have worked. Because all ferrite's the same, right? It all looks the same. And you typically, when you bought that ferrite, it had no markings on it. There's no markings on it. You didn't know what you got. I also want to talk a little bit about common mode and differential mode. If you're anything like me, back when you took your first ham license, or maybe you upgraded to general, there was a question about common mode currents or differential mode currents. You probably, like me, memorized the answer because you didn't really understand it. Common mode EMI and differential mode EMI is different, and how you fight it is a little bit different in both cases. And there are some unique things about ferrite that, especially in differential mode, that you should know. How do you pick the right ferrite mix? I have a chart here that we'll talk about that. And I have 3 slides on how ferrite is made. Most people kind of think that ferrite is kind of like, maybe it's a liquid, it's poured into a mold. It's not done that way. So we'll cover some of that. So what is ferrite? Ferrite is basically a process. We make it using oxides, either manganese or zinc. When I say oxides of manganese and zinc, what I'm talking about is rust. In other words, we don't use metallic manganese or metallic zinc. We use oxides. So basically, when ferrite is made, we take these powders, they're finely sieved, we mix them with a binding agent, and then they're pressed. Ferrite's a soft magnetic material. What does that mean? It's not like your refrigerator magnet. If I take a piece of ferrite, wrap a coil around it, put a current through that ferrite, I'm going to get magnetic flux. And once I take the current away, the magnetism completely disappears. That's what I mean by soft magnetic material. And again, there's two basic materials, manganese zinc and nickel zinc, and they have different properties. So going back to what I said earlier, when you go out to the Hamfest and you saw a pile of ferrites and you didn't know which one was which, you really need to know what you're buying. So how does a ferrite work? Basically, when I take a ferrite clamp on or a solid core and I put it around say a piece of coax, it becomes magnetically coupled into that circuit. How ferrite works is basically it will allow in common mode, if you've got it wrapped around your coax, it'll allow the target signal to pass, and the higher frequency electromagnetic interference is going to be absorbed into that ferrite and will be dissipated as tiny amounts of heat. Now, it's not heat you can really feel. It's in very, very small amounts. But basically, ferrite will absorb high frequency EMI and allow that target signal to pass through. This is a good representation of what's happening inside that ferrite. I'm going to replay that if I can, but I'm not sure I can actually. But what on the left side, you saw as the frequency went up, the impedance was changing from almost being purely reactive to as the frequency got to a high point, the impedance became almost entirely resistive. This is kind of an important feature of ferrite. At low frequencies, ferrite is completely reactive. In other words, it's got both a magnitude and a direction. At a certain point, every ferrite will become highly resistive and the EMI will be absorbed. So picking the right ferrite for the right application. Ferrite's used as transformer cores, typically at low frequencies, less than 2 megahertz. When the frequency gets above that, ferrites become highly resistive and will absorb EMI. This is a very good representation of exactly where ferrites are used. You'll see 3 different things in power, signal, and EMI suppression. Again, what I said earlier is from the kilohertz range up to maybe 1 or 2 megahertz for your high frequency switching power supplies. Ferrite is used in that application as a transformer core or a broadband signal amplifier. Inductive modes, say, if you're using it as a inductor, it'll be from a couple hundred kilohertz up to the 100 megahertz range and slightly beyond. And then suppression ferrites are used from about 150 kilohertz up to the gigahertz range. Almost all of you are familiar with solid cores and clamp-on cores, but you might not be aware of the fact that it's made in many different kinds. We make surface mount components, PC beads, chip beads, multi-aperture cores. We make solid plates. We even make a flexible ferrite that can actually bend and be used as almost like a Faraday shield inside a box. So picking the right one for the right application. As hams, we usually pick either a clamp-on or a snap-it. That's our most convenient form, but you should also be aware that they can be made into surface mount components as well. This is a chart that I really wanted to get to. Again, we talked about going out to a ham fest, buying some ferrites. It's important that you pick the right mix. This is our company's product mix for suppression ferrites. You're probably most familiar with maybe the 43 or 44 material, maybe the 31 material. Each one of these ferrites actually has a different range of suppression. You notice up at the top in the red, there's the FR75. That's our code for the low frequency suppression material. That's good from about 150 kilohertz up to 10 or 15 megahertz. Down at the bottom is our FR61. Suppression starts at about 200 megahertz and goes up beyond a gigahertz. So knowing what problem you have, what frequency range will dictate which ferrite blend you want to buy or get a hold of. As hams, we'd like to think that almost all of our product, all of ferrite is used in ham radio. Our company's estimation is that about 3% of our product goes out to hobbyists like ourselves. 97% of our product, and we make hundreds of millions of pieces of ferrite per year. It goes into various other industrial applications. RFID, if you've ever seen an RFID badge, it's got a small ferrite rod in there that's probably about a 0.5 millimeter by about 5 millimeters long. Companies that make RFID badges buy ferrite in hundreds of millions of quantity. In fact, we can't even count them, we weigh them. That's the only way we can sell them. Power supplies and transformers, if you think we all have a switch mode power supply, there'll be a ferrite core in there. Connectors, we make flat plates that go inside connectors to absorb EMI. Medical equipment, MRI machines, we sell to MRI manufacturers. If you've bought a washing machine in the last 3 to 5 years, they've gone from almost a completely mechanical assembly to one that's almost all electrical. It's got a microprocessor in there. ferrite is used in there. And finally, energy, photovoltaic, rooftop photovoltaics use our product as well, although a lot of you guys are having problems, I'm sure, with rooftop EMI. So again, only about 3% of our product ends up in the hobbyist market. I like to show this slide because we get the question all the time, something that goes like this. I'm on 40 meters. I have about a 40 over S9 noise problem. I clamped on a piece of ferrite and it didn't do any good. So I'd like to show this formula. The formula looks complicated, but it really isn't. It basically says that the amount of attenuation you can expect is basically the impedance of the load, the impedance of the source, and the impedance of the ferrite over those items. If you do the math, because we have typically a 50 ohm impedance for your transceiver, a lot of us are using a half wave dipole that wants to see 50 ohms. Once we work out the math, a typical ferrite core will provide about 5 to 8 dB of suppression. If you have a 40 over S9 noise problem, one piece of ferrite's not going to do it. In fact, 50 pieces of ferrite probably aren't going to do it. There's a limited amount of suppression that a ferrite can supply. It's not infinite. So we get that question 2 to 3 times a week. I clamped on a piece of ferrite. It didn't do a lot of good. So knowing what to expect from the ferrite that you get is important. About 5 to 8 dB is about all you're going to get out of one piece of ferrite. Let's talk a little bit about common mode EMI versus differential mode EMI. Common mode EMI is where the noise travels in the same direction down both the supply and the return. Differential mode goes down, and this is probably the most common form. EMI goes down one source and it goes back in the different direction back to the source. Common mode is difficult sometimes to diagnose and to fix because that noise is going to come back to the source either through a chassis, a ground. It'll find a way to get back there. I found out when I had my novice ticket back in the 1970s and upgraded to general. The reason I knew I had common mode is I had a D104 microphone that I was very proud of. And once I put my lips close to that microphone and touched it, I got a good RF burn. Good example of common mode. It was basically that RF is finding a way to get back into the shack. So we fight it in different ways. Common mode, basically the definition is you use a single core and both the supply and the return go through the same aperture core. Typical, for us was we'll take a ferrite and clamp it around the coax, both the center conductor and the return shield go through the same piece of ferrite. Differential mode's different. You're basically going to just put it on maybe one leg of a MOSFET that's carrying a signal and probably also a DC current. Common mode has the advantage of letting the target signal pass and will absorb the higher frequency EMI because the magnetic fields inside that core are equal and opposite and will actually cancel each other inside the core. So what does that mean? That means the core is not going to heat up. A lot of times if you're using it in a differential mode application where you've got just, say put it on one leg of a MOSFET, that core will actually heat up, and if there's a large enough DC bias passing through that line, the core will actually derate severely in impedance. And here's a good example of this. If you take a look at the impedance graph there, and different amperages are listed, 0 amps, 0.2 amps, 0.5 amps. This is actually, I believe, an FR61 core. Look how the impedance derates. If the core sees enough bias current, it will severely derate down to almost zero. In fact, it will get to the point where it will provide no impedance at all. So knowing these secondary characteristics of a ferrite is important when you pick one out. So how do you select the correct current? Basically, you have to estimate where you've got a differential mode problem or a common mode problem. Most problems hams face are common mode. Most manufacturers face a differential mode problem. How much attenuation is required? Again, using that example I was using before, if you've got a 40 dB over S9 problem, ferrite's not going to fix the problem. Do you have DC currents running through? Different ferrites react differently to DC currents. And basically form factor. Do I need a clamp on? Do I need a PC bead? We make all of those products. This is a good slide. I just want to cover this again because we talked a little bit about it earlier. We talk about complex permeability of ferrite. Again, permeability is if I take a piece of ferrite, wrap a wire around it, pass a current through it, I get a magnetic field. Higher permeability ferrites will generate a stronger magnetic field. The mu prime, the little u there with the prime next to it, is the reactive portion of the ferrite. That's where ferrite makes a good transformer core, perhaps a good inductor. Notice how as the frequency increases, and this is our FR61 material, at a certain point around 10 megahertz, that reactive portion drops off dramatically and the resistive portion starts. So if I buy an FR61 ferrite and I want to use it as a transformer core, it's probably going to work out to maybe 10 or 15 megahertz. If I buy it for suppressive purposes, it's going to work above that frequency range. So this chart just demonstrates that depending on the mix, almost all ferrites can be used in a number of different applications, but knowing the frequency of where you want to use it is important. These charts are available on the Ferrite website and on our competitor's website. Another important tool to know is that if I pass a ferrite core or pass a current carrying conductor through a ferrite core and I just wrap it around the ferrite, or there's one pass through, I get a certain amount of impedance. If I take it twice, if I wrap it around twice around that ferrite core, I square the impedance. So if I have 10 ohms with one pass through the aperture, I wrap it around twice, I have 100 ohms. It'll square again. So if you need to get more impedance out of a ferrite core, more passes will dramatically increase the impedance to the point where you'll get thousands and thousands of ohms. Just want to cover one last thing on ferrite manufacturing. I talked a little bit about it. A lot of times we have hams that think it's like a liquid that pours into a mold. It's not. Basically, every piece of ferrite that we make is done is made by forming. In other words, we have a press. Those pieces of ferrite that you see on that conveyor there, that's going into our 600-ton press. Or actually, it's coming out of the 600-ton press. It's pressed to get that, like that. Each piece of ferrite has its own unique die. So we have a catalog that has several thousand parts. We have several thousand dies that we keep in stock that are mounted in that press. That punch press comes down, punches out that piece of ferrite. Once it comes out, it's basically in what we call the green state. I can take that piece of ferrite and crush it in my hand. The next step that really forms the magnetics of the ferrite is called sintering. Sintering is basically done in two methods. One, we call it the pizza oven. It looks exactly like the pizza oven at Pizza Hut. Goes down a conveyor belt that's about 25 feet long. Temperatures inside that oven reach 2,000 degrees Fahrenheit. Small parts will take about 4 hours to go down that. And what happens in that is basically that ferrite is fired, the binding agents are driven off, and it becomes like a high strength ceramic material. Two different types. We have both we also have a box kiln that allows us to fire both in an oxygen atmosphere and a nitrogen atmosphere. Manganese zinc ferrites require a reducing atmosphere of nitrogen. So there's basically two types. A large piece of ferrite, like that block you saw in the previous thing, will take 4 days in that box kiln at 2,000 degrees to fully form. If you ever wondered why a piece of ferrite costs $5 or $6 and most electric components are about a penny, the truth is that almost all of it requires high energy or high heat. As you can imagine, those ovens are on 24 hours a day, 7 days a week. At 2,000 degrees Fahrenheit, the transformer outside the company that I worked for is about the size of all of these chairs put together. And finally, the last stage is finishing. Biggest operation here is the burnishing operation. We take each piece of ferrite, we tumble with plastic media to knock off all the sharp edges. We might gap it if it's a transformer core. We might coat it with paraline to insulate it if it's one of the manganese zinc beads. And we might also put a thermoset coating on it to do the same thing, basically to insulate it. So that's what I've got. Any questions?